Welcome. In this lesson, we're going to take a look at the Mergesort algorithm, which is a recursive and very fast way to sort a list of values. Let's get started. We've got two learning goals for today. The first is that you can explain the behavior of the Mergesort algorithm, and the second is that you can compare the speed and implementation of Mergesort to other sorting algorithms that we've already learned. In order to frame our discussion of Mergesort, let's revisit some algorithms that we've already learned, starting with linear search. Remember that the goal of searching is to find something inside an array or an array list. And linear search does this in a very simple way. It searches from the beginning of the list to the end of the list, visiting one element at a time. And it's very simple to implement. It's a loop and an if statement, but it's very, very slow for large lists because you have to look at every single element. On the other hand, binary search takes a very different approach. The approach it takes is called divide and conquer because it tries to break a big problem into smaller subproblems. Specifically in this case, what we can do is leverage the fact that if we're searching for something, say a 7, we can recognize that that's in the right half of the list. And if it's in the right half of the list, then I don't even have to look at the elements in the left half. And so every time I'm able to eliminate half of my list. Now, this is a harder to implement algorithm. It requires more complex code and the list has to be sorted. But if we're willing to do that, it is significantly faster because it's removing half the list at each step. In fact, I think during that lesson we talked about if you wanted to binary search the entire population of Earth, it would only take about 35 steps. In addition to searching, we also learned a couple of sorting algorithms. Remember that sorting is trying to put the list in order from smallest to biggest or biggest to smallest. So one of the algorithms we learned was selection sort. And the way it works is it does a linear search trying to find the minimum smallest value in the array. And then once it finds it, it swaps it to the beginning of the list. And so this linear searching for the smallest element repeats over and over and over. And because we have to do a linear search for every single element in the list, it ends up being quite slow. We also learned about insertion sort, which takes each element and compares it to the already sorted elements. And then what it does is it inserts it into place and shifts everything else to the right. But here again, like selection sort, this process can be very slow because for every element we insert, we have to do a linear search to find the insertion spot. So we do linear search after linear search after linear search, and the process for large lists can take quite a long time. In this lesson, we introduced the Mergesort algorithm, and Mergesort uses recursion to divide a list in half over and over again until the list is only one element long. And then it uses a process called merging to take these one item lists and put them back together, but in the correct order. Mergesort begins with the complete unsorted list, and then it breaks that list into two halves. We're going to keep breaking into two halves until we get to lists of size 1, and we're going to do that process starting on the left side. So we break in half, and we break in half again until we're just left with two elements, 5 and 3, two lists of size 1. And once we get to this point, now we can start to recombine them, to merge them, but in the correct order. So 5 and 3 is in the wrong order, so when we recombine them, we'll make it 3, 5. At this point, we're going to go back to where we left off with our splitting on the left side. And we're going to take 4 and 1 and break it into two halves. And again, we find that we have lists of size 1 that we can recombine in the correct order. Now, we've got two merged lists, 3, 5 and 1, 4. So now we can take those two lists and merge them together in the correct order, and we complete the left side of our list. Notice that it's sorted 1, 3, 4, 5. Now we'll turn our attention to the right half. And 6, 9, 2, 7, we'll break it in half, and we'll break it in half again until we end up with lists of size 1. Now notice that 6 and 9 are already in the correct order, so when we merge them, nothing changes. The same is true with 2 and 7. When we break them apart, they're in the correct order, so when they merge, nothing changes. But now that we have 6, 9, and 2, 7, we can merge those into 2, 6, 7, 9. Notice again, that list is sorted. And so finally, we end up with a left half that is sorted and a right half that is sorted, and we can merge those back together to complete the sorting process and end up with one complete list that is totally sorted from smallest to largest. Let's take a closer look at the merge process. The whole premise of the merging is that if I have two lists that are sorted, I can merge them into one list that is still sorted. Now remember in Mergesort, I break the list down and cut it in half again and again and again until I get to lists of size 1. So in this case, 5 and 3. And remember that lists of size 1 are sorted by default because there's only one element. So here's how we'll merge them. Look at the two elements and identify the smaller one. Of course, that's 3. Now move it to the merged list. Once we've moved the 3, there's only one element left to merge, which is the 5, so we also move it to the merged list. And once we've done that, we now have a merged list that is still sorted. Let's take a look at this merge process one more time, but this time with lists of size 2. Remember that Mergesort recursively divides the list in half until we get to lists of size 1. So 5, 3, 4, 1. Now at this point we can begin merging them, but when we merge them we want to make sure that they stay in sorted order. So 5 and 3 merges to 3, 5, which is sorted, and 4, 1 merges to 1, 4, which is sorted. And now I have two sorted lists, 3, 5 and 1, 4, and I can now merge those into one list that is still sorted. So how do I do it? Well, I'm going to look at the first element of each list, 3 and 1, and I'm going to choose the smaller number and add it to my merged list. So of course we choose 1. Next, we're going to look at the first element, 3, and in the second list, the only element left is 4, and choose the smaller to add to our merged list, which of course is the 3. So now we look at the only element that's left, 5 in the first list, 4 in the second, and we choose the smaller, which is 4. And at long last, we only have one element left, 5, so we'll add that to our merged list. And what you can see is through this process, we start with numbers that are completely unsorted, 5, 3, 4, 1, and after merging a couple times, we end up with 1, 3, 4, 5. For large lists, Mergesort is one of the fastest sorting strategies you can use. The reason it's fast is because it employs a divide and conquer strategy, just like binary search. And the whole point of divide and conquer is that we take a hard problem and we break it into smaller, easier problems. Insertion sort and selection sort tackle sorting a whole list, and that's a hard problem and it's slow. But merging two smaller already sorted arrays is very, very easy. And so Mergesort leverages that and it makes things go a lot faster. However, the trade-off for it is that the code is quite complicated, as we'll see in just a moment. So if you're going to use Mergesort, you really need to use it in a situation where speed is very, very important to you. Otherwise, insertion or selection sort will do just fine. Let's take a look at the code for Mergesort. Now, understand that there is absolutely no expectation that you have this code memorized or even that you fully understand it. What we really want to do is take a high-level view of what it does so that we know enough to be able to play around with it a little bit in the exercises. So starting at the top, we have the base case. And remember, the base case is what stops recursion. And the recursion stops when our list has size 1. So if the length is less than 2, we simply return from the method. If the base case isn't met, meaning that our array still has a size greater than 1, then we have to go ahead and split it into 2 halves. And that's what this middle chunk of code does. So it finds the middle of the array, and then it creates and fills a new array for the left half and for the right half. The next step is to then call Mergesort recursively, sending it the left half of our list and the right half of our list. The last step, once we've checked the base case, created two arrays that represent the left half and right half, and then we've called Mergesort on both of those, is to take our left and our right array and to merge them. And to do that, we use a helper method called merge, which we'll take a look at on the next slide. This is the code for the actual merge helper method, which combines the two lists into one that is still sorted. The code at the top actually goes through and looks for the smallest element and copies it over to the merged list. And then once one of the lists is empty, the code at the bottom copies the remaining elements. So again, this code is long and complicated, and there's no expectation that you would memorize it or even fully understand it, but we will have the chance to play with it in the exercises. Now that you've watched this lesson, you should be able to explain the behavior of the Mergesort algorithm. You should also be able to compare the speed and implementation of Mergesort to other sorting algorithms, specifically understanding that Mergesort can be a lot faster because of its recursive divide and conquer approach, but it's also a lot more effort to implement than an insertion sort or selection sort.